Yeah.
Okay, so we've got the recording. So it's 3 minutes early, but we're 2 minutes early, but we'll um, trim it later. Yeah, do you want to host and do the introduction for Andres, or how would you like to do this?
Yeah, we can just give a brief introduction and
Okay.
then I think we can start. I think maybe typically just let me 45 minutes for the seminar, then QA like a 10 to 15 minutes. Yeah. Let's wait until the nine. Maybe even give like 7 minutes to
That,
let possible audience
yeah,
to attend. Yeah.
that's good. One more announcement would be just a reminder to people of the upcoming who will be presenting next, if we know the next presenter, and then we'll follow up with an invite.
Yeah, that's good. That's good. That's a very good idea. Yeah. Okay, there's okay. Hmm. Oh, great. Maybe give another few minutes.
Tom, how are you doing?
You mean
Tom Bratton?
Oh, there, I was looking for the mute button and I was not muted. I'm
Tom,
doing well.
I was reading some of your papers the other day for some geothermal wellbore work. Um, just to let you know that your legacy work still lives on.
Oh, wow. Yeah, you know, geothermal, I think is important and, you know, um, all this hydraulic fracturing, I mean, this is clearly, I think the way to, connect an injection well with a producing well. Uh, So it's exciting to see the work going on there. I wish we had more logging technology that worked at those temperatures.
Yeah, I was looking in particular. You had some. I'm working with some FMI imaging, wellbore stability um, calculations, and was looking at some of your logic from back then. It was pretty cool.
Well, I appreciate that. Thank you. Yeah, this wellbore
okay?
stability, this ought to be an interesting talk. There's, I'm doing a lot more work now in carbon storage, and I worry about uh, the the leak paths around the wellbore. I think that's much higher risk than is currently um, estimated in the industry.
I think that's a bigger discussion to have is the different cement technologies that can be utilized, validating cement bonding and distribution. I think you're hitting one of the highest risks we have.
Yeah, I mean, the damage that's done near the wellbore during the drilling and cementing process, the cement can actually be a pretty good seal, but then it degrades with time, and but the leak path is probably on the backside of the cement, and next to the formation, and that's very difficult to quantify with bond logging technology.
Well, we should line up a discussion. It'd be good for ARMA. Like maybe we have a discussion or something like that, like a meeting, and just kind of have a brainstorming session for individuals to talk about items like this. I don't want to detract from Andre's presentation. Yeah, I'll let you kick
Yeah,
things off.
I think, yeah, very interesting discussion. And I will start to introduce our first speaker of this year. Okay, Dr. Andreas Michael is an assistant professor of petroleum engineering at the University of North Dakota. He is also serving as a faculty advisor of the local ARMA student chapter. And today we are very happy to have Andreas here to introduce his exciting research. So please start.
Thank you, Yao and Eric, for letting me present for a second time for the ARMA Future Leaders seminar, and thank you everybody for attending this talk. The first time I presented was December 2023, and it was about hydraulic fracture initiation modeling. This one is a little bit of a different topic. The title is Seafloor Broaching Prevention After an Offshore Well Blowout. It's a little bit of an intradisciplinary petroleum engineering topic, I would say. It centers on rock mechanics, but it has a lot of overlaps with adjacent subdisciplines such as reservoir engineering, production engineering, wellbore integrity for sure, etc., etc. Before I dive into the details on the technical details, a little bit about what I do here at UND. I teach, in the fall, I'm teaching drilling engineering and petroleum geomechanics. These classes are consisting of 4 modules. And on the spring, I'm teaching advanced drilling engineering with well completions and advanced stimulation techniques. Generally speaking, the spring semesters are longer, so those classes consist of 5 modules. And the way undergrads are going through in their curriculum through those courses are they first take drilling, then advanced drilling in their junior year, and then in their senior year, they take geomechanics followed by well completions with advanced stimulation techniques. In my classes, because UND takes online enrollment very seriously, I make use of an online, iPhone app drilling simulator for the class. And it's a very practical teaching tool for online students. And we can use it to present examples in class and also assign projects. It basically costs a few dollars, but it's basically doing more than 90% of what the online, the in-house, very expensive simulators are capable of doing. And it's a proper utilization of digital transformation. I make all the videos of my exercises that I go through my class. I have them available online on YouTube, actually. So I am currently supervising 4 graduate students. 3 of them are purely PhD students, and one of them is dual master's and PhD student. And I have 5 projects underway. I used to advise 5 students. We have a specially designed manifold, which is used for multi-stage fracture treatment in the lab, and we use transparent gelatin blocks so we can see the fractures growing through the medium. We also have an integrated study on formation damage induced during EOR in carbonate formations. We look at one carbonate reservoir in North Dakota called the Red River Formation. We also have a semi-analytical, semi-numerical study on hydraulic fracture initiation modeling. And today, what I'm going to be discussing about is project number 2 and project number 3 a little bit, which is underground blowout prevention after offshore well capping and mechanistic modeling of wellbore integrity, looking at the casing cement shed rock formation system. So I have here 6 papers, 5 journals, 1 conference paper that contain stuff related to this topic. It all really started with an AGU abstract in 2018 in Washington, D.C., followed by an ARMA paper in 2019 in New York. And I had transferred for my PhD from University of Texas to Louisiana State. And my advisor at the time, Dr. Gupta, had won an award from the National Academies of Science, Engineering, and Medicine. It was a Gulf Research Program Award. And we started working on this topic, and I have been working on it since. And to be honest, there is still meat on the platter for about 5 more journal papers. And I have a student working on this topic, and hopefully the end game will be a patent filing. So we will start by going back to 1969, Santa Barbara, January of 1969. Union Oil was drilling a inclined wellbore in the Santa Barbara Channel, targeting a pocket, a hydrocarbon pocket. And it was a fairly easy, a mainstream well, to be honest. And because of that, they obtained a waiver to case only a shallow section of that well. If you see here, it was only 250 feet was cased. The rest of it was exposed open hole section. So in, I think it was January 28, they suffered a blowout. And it was a it was a bad accident, but it wasn't a terrible accident. The right people were there at the right time, and they started working on it as soon as possible. And the problem was that when they capped the well, when they tried to cap the well, there was this whole open hole section underneath the casing shoe that led to fractures initiating, tensile fractures initiating from this open hole section. And because this is an environment of high tectonic activities, a strike slip stress regime, the faults didn't help a lot, but they led to all this oil from the reservoir making its way to the seawater, creating a massive ecologic disaster that was visible on the surface, as you see from this satellite image. It's a colorized image. You see what the reporters at the time called oil buildups next to the platform. So it was basically oil from the reservoir making its way to the seawater from not from the well, but from areas adjacent to the well. And it was a massive ecologic disaster. It led to, I guess, an environmental movement which was already taking place. It added to it, and it led to the Earth Day in 1970. And as I tell my students in the class, this event alone is basically the main reason of why they cannot get a job in California these days. I mean, the offshore drilling has been severely affected. The offshore drilling industry in general has been severely affected since. Now, if we move 41 years later in what is now known Gulf of America, back then it was Gulf of Mexico, there was the Macondo incident in April 20th. And once this happened, there were fears of the same situation arising again. When they were able to cap the well, there were fears that seafloor broaching will take place again. Also, that was due to the prolonged discharge. The well was flowing 86 days before they were able to cap it. So there were fears that there were some rupture disks placed on the casing, or sorry, on the liner, that at about 9,000 feet, something like that. And there were thoughts that they were heavily abraded because of the post-blowout discharge, the prolonged post-blowout discharge with all the sand that was flowing through. So there were fears that this will lead to, this rupture disk will burst during after they capped the well. So the government put together a team. It was called the well integrity team. It consisted of engineers from BP, the national academies, several USGS, several big people, and they were tasked with basically trying to predict what will happen after the well is being shut in. And they came up with a plan of that they are gonna shut in the well and observe the pressure buildup. If the buildup is above a certain level, it will mean that the well is safe and there is no leaking. If the pressure plateaus below a certain level, it would be unsafe because that means they would be having a leak somewhere. And there was a sort of middle ground that they said, if that's the case, we will wait and observe. And that's what happened. The pressure plateaued at that middle ground. And after careful observations, they figured out it was okay to proceed with permanent killing of the well. One good thing that came after this incident was that the laws for offshore drilling changed in a way that nowadays, if an operator wants to drill an offshore well, they will have to make some calculations before spudding that well, which is called the worst case discharge predictions, abbreviated by WCD. And these are basically calculations of if you are going to have a blowout, these are the flow rates that you are expecting. And these are the volumes that you expect at a given time period. So if I'm going to drill a well at a particular location and I have a blowout, I know in advance what kind of flow rates I'm going to be facing and as well as volumes. So I know how to deal with it from a contingency planning perspective. And this research topic is centered on how to make better use of those worst case discharge predictions, because as an operator, you are forced to make these calculations. Now, how are you gonna be able to make use of them in a smart way to help your contingency planning? So what happens after a blowout? This is a schematic from USGS for the bottom hole pressure of the Macondo well during the aftermath of the blowout. Before the blowout, you are drilling in ballast conditions. So the wellbore pressure is equal to the pore pressure outside the wellbore. And after you suffer the blowout, the pressure inside the wellbore drops dramatically, and you are basically producing at the highest possible flow rate, given the reservoir capabilities. This is what the WCD estimations are about. The pressure is dropping, and you are producing as hard as the reservoir can produce. Then you install what is known as the subsea capping stack on top of the damage blowout preventer. And the subsea capping stack works very similarly to, operationally speaking, how the blowout preventer works. They call it the big brother of the blowout preventer, although it's smaller. It has rams, it has chokes. It works basically the same way as the blowout preventer is working, and is intended to facilitate the shut-in of the well. So you are gonna have the subsea capping stack installed on top of the damaged blowout preventer, and then facilitate the shut-in at a predetermined schedule, number of steps, and period, time duration, at that time, the pressure inside the wellbore is expected to rise. It's not going to rise as high as the original reservoir pressure due to depletion, but at that time, at the same time, the fracture pressures at particular locations like the casing chute depth or any point higher up that has been vulnerable to damage during the discharge period is also going to be affected by the pressure depletion. So they are going to change as well, the fracture pressures. So you don't want the pressure during the buildup after well capping to exceed those fracture pressures, because that means you're going to have a fracture initiation, and after that you may have propagation all the way to the surface and broaching. This is the capping stack that was used in the Macondo well. And ultimately, what this boils down to is a material balance problem. We have coupling between reservoir depletion and near wellbore geomechanics, along with well construction and wellbore architecture, in order to predict underground blowouts after the subsea capping stack shut in. During my PhD at Louisiana State University, I came up with the concept of critical discharge flow rate, something that can be used as a yardstick to predict an underground blowout at a specific time after a shut-in, which takes place at a specific time after the blowout for a specific kind of fracture at a specific depth, It is used to assess the effectiveness of a shut-in schedule. If the shut-in takes place at a specific time, this I can come up with a critical discharge flow rate and use it to know if it's gonna be effective or not effective accordingly. And this critical discharge flow rate can be compared against the WCD estimation to tell me in advance if I'm gonna be successful or not. So I can try, ideally, test around some different shut-in strategies and come up with a good one that will work given the circumstances. Ideally, this is something that should happen before the well is even spotted. So just like you have to do WCD estimations after you spot the well, you can also come up with the procedure that you are going to use to shut it if you get a blowout. Or if you do have an indication after the blowout of the actual flow rate taking place, you can use that as a better way to compare against the critical discharge flow rate and know if you're going to be successful in capping in your well or not. One thing I want to mention here is that there is two different fractures that we are interested at. One is transverse fracture initiation, like the blue fracture on the left, which initiates orthogonally to the wellbore, or the red fracture on the right, which is longitudinal fracture initiation and initiates axially to the wellbore. These are the same fracture initiation mechanisms that we see when we try to stimulate a well. So when we do hydraulic fracture job in the field to decrease the permeability around the wellbore, these are the kind of fractures that we are trying to initiate. They are tensile fractures. They are basically what geologic dikes are, magmatic intrusions through the rock. It's the same DNA, it's the same fracture initiation mechanism. So it's basically a problem that requires coupling of geomechanics and fluid flow. Same thing as we do for hydraulic fracturing, basically. We need a model to look at the stresses at locations of interest on the wellbore, on the borehole walls, or any place on the cased hole section that has been vulnerable to failure after the prolonged discharge. We look at the stresses on the near wellbore region. Those are the axial stress, sigma ZZ, the tangential stress, sigma theta theta, and the radial stress, sigma RR. Those depend on the in situ stresses, SV, SH max, SH min, that are dominant in the far field region. I have the axial stress color blue because that's what drives transverse fracture initiation. I have the tangential stress colored red because that's what drives longitudinal fracture initiation. And I have also the radial stress here, which is green. Actually, this is what drives debonding, and that's what creates microannuli. But that's beyond the scope of this presentation, but it's also an important stress. And of course, there is no shear stresses on the wellbore radius. On the reservoir side, we need to have a reservoir model to predict how the pressure will vary in the near well vicinity. And I have an in-house reservoir simulator that I coded on MATLAB after my PhD, and I wrote an article on the way ahead how to build your own reservoir simulator in 2021 on that. And this is what we are currently using. But you can get as complicated as you want on any of the two sides of the problem. You can write, say, a numerical model on FLAG 3D for the geomechanics side. You can use a highly specialized reservoir simulator for the reservoir side. It's gonna let you use more complexity to your workflow, add more complexity to your workflow, and ideally, we would like to have one model at the very end that can do both at the same time. Because otherwise, what we are now doing is basically forward coupling. But yeah, ideally, you can do something like they do in ResFrac, where you can have one code that is doing both at the same time, like geomechanics and fluid flow. But similarly, as we said, we can add as much complexity as we want. We can simplify the model to as simplistic case, as simple form as we can, to be able to understand how these critical values work. So let's take Horner's equation for wellbore pressure buildup after the shut-in. This is what we call PWS, and it's something that we learn in well testing and reservoir engineering classes, is that the wellbore pressure buildup, PWS, after you shut in the well, depends on the initial reservoir pressure, pore pressure, PP ini. The viscosity of the oil is mu, the formation volume factor is B, the permeability is K, the height of the reservoir is H, and you shut in the well after a period of time indicated by TP, production time, and you look at how the PWS would vary at a time delta T. Now, the rate you have been producing is given by QDs, that's the discharge rate. And this is what WCD predictions are trying to help us estimate, basically. Now, we can take Hubbard and Willis equation for the fracture initiation pressure after for a vertical well. And this is basically for a longitudinal fracture initiation. That's the red fracture on the right. It's basically taking the expression for the tangential stress on the wellbore radius, setting it equal to the tensile stress of the rock, minus the tensile stress of the rock, and then solving for the wellbore pressure, setting the wellbore pressure equal to the fracture pressure, basically. So it's a very simple expression. Now I can take these two equations, set them equal to each other, and solve for QDs. These QDs will represent a critical value, what we call the critical discharge flow rate. That is given by this closed form expression for this simplified version of the problem, of course. The real world is much more complicated than this. But what does this crit represent? So if my actual discharge flow rate is higher than the critical discharge flow rate, it means that the shut-in wellbore pressure at a time delta T will not exceed the fracture pressure. That means I'm not going to have fracture initiation, and it means I'm safe to shut in my well. If, however, the discharge rate is smaller than the critical discharge flow rate, it means that my shut-in wellbore pressure at time delta T will exceed fracture pressure, and that means I'm going to have a fracture initiation and possibly broaching as well. Now, whether the fracture initiation will lead into broaching is a separate study that we had a master student in LSU that did this project and actually published his work in the SPE journal. But that's where you are in trouble because your discharge flow rate, basically your reservoir depletion was not enough for your shut-in to take place safely. And that, of course, depends on several parameters, including time-related parameters such as TP and delta T. Negative critical values are possible because they basically indicate that you can shut in the well in any way you like, and you are not going to have any problems. So it's not an unrealistic result if you get negative critical discharge flow rate. Now we show both effects of geomechanics and fluid flow on what we call allowable stress diagram, which is from Nelson's, inspired after Nelson's work from 2005. It starts by Zobac's stress polygon, which has SH max normalized by SV on the vertical axis, SH mean normalized by SV on the horizontal axis. The dotted diagonal represents the line of horizontal isotropy. So anything below the dotted diagonal is impossible because SH mean will be bigger than SH max. And then we have the solid lines, which represents the frictional limits based on the Moore-Coulomb failure criterion. That means basically if your stress state is outside this polygon, you are gonna be having an automatic shear slippage on a pre-existing fault, which is basically an earthquake. It means that that stress state is unstable and cannot exist, or is not likely to exist based on the assumptions behind the Moore-Coulomb failure criterion. I have here two polygons, one representing the frictional limits for mu, the friction factor equal to 0.6, and one representing the frictional limits to 0.8, which is according to Barley's 1978 findings. I take this stress polygon and add two lines to it. The red line for the stress state at the wellbore radius equal to 0, and the blue line for the stress state on the for the axial stress on the wellbore radius equal to 0. That's basically assuming that the tensile stress of the rock is 0. And I plot them on the polygon, and it now becomes what Nelson calls allowable stress diagram. The area behind those lines, either of the two lines, represents stress states that where you will have a failure, given the conditions of the blue and red lines. You're going to have basically either longitudinal or transverse fracture initiation or anything in between. So an echelon-like fractures of the wellbore are still possible. Now, I just need to see where my stress state is, and I can tell if there is a fracture or fracture initiation or not. If my stress state is here, I'm safe. I don't have fracture initiation. If the stress state is here in the yellow region, I'm not safe. I have fracture initiation. Okay, this was a simple way to show both effects on one simple plot. Now, how, operationally speaking, how can I use that to facilitate, to engineer a successful blowout contingency plan? I have three parameters changing after a blowout. I have my fracture pressures changing because of pore pressure depletion, both longitudinal and transverse. I have my in situ stress state changing, not by a lot, but still changing. That green dot I had in the previous slide would be moving. And then I also have the frictional limits changing. So the size of the polygon itself is changing. So three things are taking place at the same time. And they are all seen on this polygon. The size of the polygon is changing. The lines, the fracture lines, the blue and red lines are shifting. And the dot would be changing position. So I can play with my subsea capping stack shading, the number of steps, and the step duration, and even what time the shading is implemented, to show, to be able to come up with a subsea well capping strategy that will facilitate safe shading of my well. So I can have what we call either a single step, which is an abrupt shading, which take place with one step, or a multi-step, an incremental shading that takes place over a number of steps, or I can do what we call cap and restrain or cap and divert, such that I choose a strategy that will provide me a safe shading of my well. So an incremental shading is shown in this diagram with a solid line. You see the stepwise gentle shading of the well, which takes place in 5 steps over 24 hours. Compare that with the dotted line, where which shows the abrupt shading, like immediate shading. Some people like calling it hard and soft shading, but drilling people don't like this terminology because hard and soft shading means something very different to them. So we call it incremental or abrupt. Now, how does that translate on the shading pressure buildup? It's very similarly. It leads to an abrupt shading with a dotted line will lead to an abrupt pressure buildup, and an incremental shading will lead to an incremental, gentle, more gentle-like pressure buildup from your well. Of course, there are some other factors that need to play a role, because while you take your time for this incremental pressure buildup, there is a lot of abrasion taking place, and this oil that you are producing, you need to do something with it. You cannot let it flow into the seawater. But and mathematically, we can model this. Pressure buildup using Matthews and Russell variation modification of the Horner's equation, which I have here. It's on the first SP monograph, first page of chapter 6. It looks very similar to the Horner equation, and it's actually it's an analytical model which has its own problems, of course. Now, assume that delta T goes to infinity. What will the PWS become equal to? Is going to be PP in. This is because they assume an infinite reservoir. That means any oil that you produce from that reservoir will be replaced. Either you have a large aquifer which flows into your reservoir while you are producing, so that keeps the pressure on the long term maintained, or you have your reservoir is so big that for the amount of time that you have been producing, that won't make a big impact on the pressure. This is not unlikely to be the case in real life, but it's not always the case. So we have to use a reservoir simulator model or a reservoir simulation model that can take account of these finite reservoirs in order to be as realistic as we can. And my current student who works on this topic, his name is Abdel Hakim Quisat. He has written, I think, 2 journal papers and has 2 under review and 3 conference papers on that topic. He started looking at it from a mass perspective instead of a rate perspective. So we look at how much mass is removed from the reservoir in total rather than what rate is this volume removed. Because if we take the integral of QDs with respect to time, it's basically volume. And volume in standard condition is mass. So we look at this M star is basically the value of mass removed from the reservoir during post-blowout discharge. And we come up with this critical discharge mass, which is not an official term, but is basically compared with M star. If M star is bigger than this critical mass, it means that we are safe to shut in the well. And if it's less, we are not safe to shut in the well. Again, we are sensitive to time. So the time that you shut in the well after the blowout is important. And the time that you are looking for the pressures after the shut-in is also important. So it affects a lot. If I shut in the well after a blowout today, I'm gonna have one critical value. And if I'm gonna shut it in 2 days, I'm facing another critical value, the same well, because I have 48 hours of additional discharge taking place in between. So the whole analysis changes. But again, I can use these terms to compare strategies. So in order to see the impact of the discharge flow rate trend after the blowout, I need to compare it for considering a equal mass removed from the reservoir. And here in the diagram, it's from a paper that we had in last year's Offshore Technology Conference. We have 4 different discharge flow rate trends that all of them yield the same mass, add to the same mass, and they all have the same TP. The shut-in takes place at the same time. So what happens because of mass balance is that the pressure will build up ultimately to the right, to the same value. That is neglecting wellbore storage effects and water hammer effects, which we do not have in our model. We need to incorporate a transient wellbore model for that. But also, if we use a different shut-in time, but again, the same mass, the same total mass discharge, again, they are gonna rise. The pressure will build up to the same value ultimately. But the lower, the steeper the decline before the shut-in, the bigger the jump. And also the bigger would be some other effects that are not incorporated, like the water hammering, etc., etc. Correlations can be drawn for the valleys of this plot, although this is not as interesting as some other correlations that I'm showing here. This is basically a pressure response curve, as we call it, for a blowout that basically we use this example to show how you can decide on what strategy to implement based on what happens, based on these concepts that I described in the previous slides. So suppose you have a blowout at time 0. The pressure inside the wellbore will follow this green line. Okay, the dotted blue lines indicate the fracture pressure at bottom hole value equivalents for different casing shoe depths of that well. And we have the pressure with the red line. We have the pressure response after you shut in the well 14 days after the blowout. So say I was able to install my subsea capping stack 14 days, 2 weeks after the blowout. If I shut in the well at that time, the pressure buildup will exceed the dotted blue line for the casing shoe at 13,111 feet casing shoe depth. That means I'm going to have fracture initiation, which is not good. But what if I'm able to divert 24 more days of discharge? Now, this is not oil amounts that should end up inside in the seawater, but say I have a sea vessels coming over to pick up this oil or some sort of facility for storing this production for 24 more days, which is not a small amount of time. And I'm able to shut in the well at day 38 after the blowout. For reference, Macondo well was shut in 86.2 days after the blowout. So if I shut in my well at that time, 38 days after the blowout, the pressure buildup will not exceed this fracture pressure. So I'm gonna be safe to go for a permanent killing of the well after the shut-in. And this diagram can be used, and these are numerically obtained results, can be used to create pressure response for different time periods, different points. If I shut in the well at 14 days, 26 days, 38 days, 56 days, 68 days, 86.2 days. And we call this the spider plot. And the response also on the fracture pressure is shown with the blue lines on the top. And then we pick up arbitrarily a point on this curve that we call the plateau pressure. And this is completely arbitrarily. It is shown by the star here. It's basically the pressure at which the pressure change after that is less than 6 psi per day. That was for this paper, but it can be 4 psi per day, it can be 10 psi per day. Is completely arbitrary. It basically tells you the pressure doesn't build up by much after that. And this is what we call plateau pressure. And this is what we are sort of targeting with these correlations. We have a correlation for the fracture pressure, a correlation for the plateau pressure with the dotted orange line, and for the wellbore pressure during discharge for the green line, the green solid line. And we can derive a correlation for the time at which this plateau pressure is reached, that delta T time against the time from the blowout, the post-blowout discharge, and the remaining connected volume of the reservoir, which is something that is important for something that practitioners can easily use. But the real end game is this plot, which is basically shows the critical discharge from the reservoir on the horizontal axis and the plateau pressure on the vertical axis. So for example, if my PFRAC, my fracture pressure is here, I read from the diagram the critical discharge mass, and then say if, for instance, my actual discharge was less to that yellow M star value, it means I need to take care of this extra mass of discharge before I'm able to safely shut in the well with the proposed shut-in strategy. So going forward, we want to design a simple and effective workflow that streamlines the selection for the response to a blowout, an appropriate response to a blowout. It's gonna likely be graphical and involves tables. We want to compare the critical values of discharge and mass, in particular mass, against several independent variables related to geomechanics and fluid flow and wellbore architecture, and make it easy for practitioners to use in their office or in the field. We want to incorporate more realism to our models, such as wellbore storage effects and water hammering effects. We can use modern-day data analytics to derive universally applicable, basically play-agnostic expressions that can use in practical format. And of course, all this is applicable to onshore scenarios as well. It's not just offshore. This was an offshore well project because WCD is mandated by law for offshore wells, but I know several operators, like I heard Chevron, for instance, they are calculating worst case discharge even for onshore wells. So this is possible to be applied to onshore locations as well. And with that, thank you very much. I want to acknowledge all the funding sources that we had on this project so far. My old advisor at LSU, the student who works on this project in UND, and of course, Yao and Eric for letting me do this presentation. And with that, thank you very much. I would be happy to answer any questions.
Okay, thank you, Andreas. So questions from the audience?
Andreas, where do you see this going next? Like if you were to, the next iteration, if you're going to make an improvement on this or application, like where do you think you take this work next?
Yeah, that's a very good question. I would say you can progress this model on either of the two sides of the project. You can progress it on the geomechanics side or from the reservoir side. I will say personally, I think right now it's more developed on the reservoir side than the geomechanics side. But there are several ways you can move on. Like you can add complexity to the geomechanics model as much as possible. You can add complexity to the reservoir model as much as possible. One good way to move forward is to write a wellbore transient model and couple that with a reservoir simulation model. In that case, you can see the added pressure buildup from water hammering and wellbore storage effects. So there will be some spikes, like I have a backup slide here for some spikes. If you see in real life, you are expecting to see some actual spikes when you do the shut-in that are short-term spikes, and they are basically due to afterflows. And this can do damage because that can exceed. You may be expecting not to exceed the fracture pressure, but then you might exceed the fracture pressure because of those spikes. So this is something that I would like to incorporate in my model in a broader sense. And that will require basically coupling a wellbore transient analysis to it. There are other ways from the geomechanics side you can proceed. We can see, for instance, wellbore integrity in the cased hole section for specific studies. Like if you have a specific wellbore architecture, we can build, say, in Flag 3D, a very detailed model that includes the cement, the casing, and then try to see how does the pressure build up, do dynamic analysis basically, and see how the pressure buildup will be reflected from a well integrity perspective. Is the cement shed gonna hold, or is it gonna break? If it's gonna break, what kind of failures we're gonna have and at what depth, etc., etc. And then obviously another way to proceed is to investigate, okay, if I'm gonna have a fracture initiation, how far will these fractures propagate? Will it be a broaching incident on the mat line, on the seafloor, or not? And take it from there. And there have been a lot of studies that took place on that regard. And Gulf of Mexico is not like Santa Barbara Channel. It's more normal faulting stress state, is less tectonically active, is not likely to get a broaching incident. It's not as easy as a tectonically active environment, but it's still possible.
Andreas, that's a very good presentation. I really appreciate the information. I hadn't thought so much about the failure mechanism where you kind of initiate along a bedding plane or the horizontal uh, uh, failure mode, but I have seen that, but you have to be in some pretty high tectonic regions for that to happen. But it's certainly possible. Very good talk. I appreciate the information.
Yeah, thank you, sir. Yeah, it's a lot of things are down to the wellbore architecture, which is it depends on operational procedures, is the stuff that human put downhole, the casing they use, the cement they use. There is several parameters that will impact the integrity of the well as a whole um, from a holistic perspective. I have a tangential study on this topic, which looks at the integrity of the casing, cement shed, rock formation system, and we look at the three layers discretely. So we look at failures in the casing, like burst, collapse, and we look at failures in the cement shed, like debonding, radial cracking, disking, um, shear cracks, and we look at obviously failures like the ones I talked in this case, like a longitudinal fracture initiation, transverse fracture initiation in the rock formation region, along with even fault reactivation. But yeah, I mean, for this project, we look at basically the casing shoe or something a little bit above the casing shoe where we think that has been vulnerable to failure.
Thank you.
Thank you.
Andreas, indeed, I have a question because I see you have the stress diagram, which is very interesting. So could you give a comments about the in-situ stresses impact on your results in this problem?
Yeah, thank you for this question. Yeah, so as you know, when we drill a wellbore, we make a hole in the ground, we remove rock, we replace it with fluid and some other equipment. So we disturb the stress field. And when we are near the wellbore, the stresses that matter is the cylindrical stresses, the near wellbore stresses. The radial stress, sigma RR, the sigma theta theta, sigma ZZ, which we know their equations. There is a long story of how those equations were derived. It started from Kirsch in 18, actually no, it started from Lamé in 1831, which was they were doing experiments on they were doing work on cannons in France, and then it went to Kirsch in 1898, and then from Kirsch it went to Hubbard and Willis in 1957, and from there I think it was Heimson and Fairhurst 1967. So it depends on as the time moved on, every iteration of these equations had more complexity. I mean, the versions of the equations that we use incorporate linear poroelasticity. But the bottom line is that you really want to know what happens stress-wise at the location that you think the fracture is going to start. So you are looking at the wellbore radius at basically R equals RW, and you want to know the value of the stresses at that particular location. And for that, you will need to know the pressure inside the wellbore. So you need a fluid flow model. And you also want to know the pressure outside the wellbore, basically the pore pressure there at that location specifically. So yeah, I mean, generally speaking, we use, because they are tensile fractures, what we are discussing, if this sigma ZZ or sigma theta theta become more negative than the tensile stress of the rock, we have the corresponding fracture. It will be transverse fracture for the axial stress. It will be longitudinal fracture for the tangential stress. And then you have debonding possibilities based on the radial stress, which I don't talk on this. I didn't talk about on this topic, but this is how you get the microangulus.
Okay, thank you. And my another question is like, in your assumption or in the real blowout, will be only one fractures or more than one fractures?
That's a good question. I mean, you can have, I mean, in California, they had, I think, 5 observed fractures that made it to the seafloor. So, I mean, I bet you there were many more that didn't make it to the seafloor. So, but there they were dealing with a massive open hole section, and you can have fracture starting from any point on this open hole section. The easiest place to start a fracture is right below the casing shoe, because that's where the fracture pressure is supposed to be the smallest. And then if the reservoir is supplying more and more pressure, you are gonna keep propagating those fractures to make it to the sea floor. Now, in real life, you have heterogeneities and isotropies to deal with, so it might be the only place directly below the casing shoe. You may have fractures starting at any point along this open hole section, or even above in the cased hole section if you have damage. So I would say the shallowest, most vulnerable section is the one that is most likely to yield a fracture. And then just like when you stimulate a frac stage in the oil field, you can keep getting fractures for as long as you provide energy for. In this case, the energy is not provided by you on the surface, it's provided by the reservoir. So that's why when this incident happened, they were basically hopeless until the reservoir depleted. So they were basically they were dealing with oil boil-ups from, I think, January 28 until February 12, when they were able to finally cap the well for real. And they were having issues even after the well was capped. They were having oil in the seawater after the well was capped. So ultimately, reservoir depletion is the key. If you get to this situation, I mean, if you get to a broaching situation, there is not much you can do.
Okay, thank you very much. And thank you for everyone for attending. And we would like to announce our next speaker will be our counter president, Dr. Andrew Bunker from University of Pittsburgh, and it will be happened in March 13. Yeah. Okay. Thank you, everyone. Have a nice rest of the day. Yeah. Thank you,
Thank you.
Andrews. Thank you, Eric.
Thank you, everyone.
Yeah.